Hi, it's Robin. Here's my Commodore PET Model 4032 running a smooth scrolling text banner. I made this for Jessica and Michael, who are getting married soon. They had seen another video I made demonstrating this routine and contacted me to see if it was possible to customize it. They're planning on having a couple of their pets at their wedding reception and wanted an interesting display for their guests to see. Unfortunately, due to the pandemic, the party is going to have to be postponed until next year now. But the wedding is going ahead, and I was happy to make this for them. And I wanted to make a video showing how this works anyway, so we'll head over to the Commodore 64, and I'll show you how I made this and how it works. So I'm here at my Commodore 64, and first to make the scroll text, I've got what is sometimes called the 3-in-1 editor by Anthony Crowther, also known as Tony Crowther, a very prolific C64 game developer in the 80s. And I first found out about this editor when I happened to buy this Your Commodore magazine in April 1990 when I was on a trip to England. I was pretty thrilled to find a Commodore 64 magazine still going, so I grabbed it. And if you're wanting to use this editor, there's instructions in the magazine, 3-in-1 Plus, on page 65, and you can find this magazine on archive.org. So we'll go into the character screen editor, and there's a number of steps to get ready. Press F7 for the menu, choose the window size. We're going to go with 00FE, which is the limit of what my routine can handle as far as number of characters, and a height of 7. It's a 16-bit hex value. So we've set the size of the map, and we've got to set a couple other things here. We're going to choose high-res graphics. We're going to fetch characters, which you could load in a custom character set here, but we're going to get the one at D1000, which is the character ROM built into the 64. We're also going to fill the window with the blank character, which is hex 20, 32 decimal. That's a space. We're going to set the border character to FF, just so there is a border. We're going to press J to jump from the character editor into the map. And there we are in the map on the bottom part of the screen. And we're going to press plus to scroll all the way up to character A0, which is a reversed space. There it is. I'm choosing this editor just because I'm kind of nostalgic about it. It's really old school. You're welcome to use a different tool if you ever want to draw a map on the 64. Okay, and I want to leave 40 blank characters at the left edge of the screen. And there we are. And now I'm going to get drawing. G lets you grab a different character, which is a lot more convenient than scrolling through the characters again. Almost all those Commodore 64 games that you love were pixeled by hand with far greater skill and detail than what I'm doing here. And many of those games were just made exactly with this sort of, well, sometimes this tool exactly, or a tool very similar to it. So if you find this tedious, I guess just think of all the work that went into the games that you love. Maybe Twitter told me this was the best way to draw a heart. Okay, that is done. And now we're going to save the window. The save file, I'm just going to call that map2. Okay, now that that's done, so I've got this program in BASIC. There it is. I'll run it. So just for the sake of example, this is a single row that will scroll. Each time I go to 200 in this BASIC program, it's going to transform everything in that row. Did you see how it all shifted over? And now it didn't move that time. I'm going to talk about that in a bit. But there, it moved again, go to 200. And it didn't move again, but there, now it's back to the origin. If I go to 600, it's going to colorize that top line, alternating blue or cyan and white. And now we can go to 200 again. I think this will make it more clear. See how it shifted over? And you can see that the character and color cells are where they are, but the characters give the appearance of being shifted over. Do that again. You see how it's moving along. And it looks like it's scrolling, but all we're doing is using the PETSCII characters built into the C64 and the PET to give the appearance of scrolling. This program's just a collection of demonstrative little examples. So when I go to 400, it prints out this list of the screen codes, 96. So this is what 103 looks like, 106, 118, and so on. They're not linear, but these are the screen codes that when this value of 244 decimal is poked into screen memory, this is the character that results. All the cursor does on the Commodore 64 is toggle the high bit, which in the case of the built-in C64 ROM is the inverse character. There's really just 128 unique characters in the C64 character set. Essentially, it's like this is character 103, and if you add 128, you get 231, and that's this character right here. They're just the inverse of each other. All the 0 bits become 1, and all the 1 bits become 0. Now, I only just realized that on the Commodore 64, this is kind of an aside, characters 103 and 106 are identical. You can see here. But I'll run this on the PET, and you'll see that 103 is actually skinnier. It's just a single pixel wide, while 106 is 2 pixels wide, as we see here. When they took the character set from the PET, transferred it to the VIC-20, transferred it to the Commodore 64, on the Commodore 64, they doubled up single pixel lines because they didn't appear very well on a TV set. A lot of Commodore 64s originally were used with TV sets. So they went through and wherever there was a single width character line, they doubled it up. That's good in your regular alphanumerics because it probably really would look terrible on a Commodore 64 if these were just a single, if the lines that made up these letters were just a single pixel thick, especially on a TV set. The PET had a crisper monochrome monitor, so that wasn't a problem for it. But I think it was a mistake doing it here because you've ended up with these characters just not being as useful. My routine here depends on character 103 just being a single pixel and 106 being double wide. 118, this is 3, 4, 5, 6. And you see they've done the same thing with these two characters. 244 and 229 are the same as each other. It doesn't cause my conversion routine here to break, but it doesn't look as good. It doesn't look as smooth. So fortunately, this will work fine on the PET. And that's why when I go to 200, the second time, it doesn't appear to move at all. And then here it's all scrolling properly. Now this one won't move either. Just looks like it stayed the same. Those are different characters now. They have been transformed, but they look the same. Now it snaps back. So just to explain a little bit of what's going on here, this big nasty array is the magic behind this scroll routine. Character 32 is just a space, and it gets transformed back into a space. Character 96 looks just like a blank space. It's actually a shifted space. And it's absolutely fortunate that the Commodore 64 and the PET have this, because I don't think I could have written this routine as tightly. It probably wouldn't look as smooth. So I'm using 96 as the shifted space as a flag, essentially, that 96 will get transformed from 96 into character 103. Character 103 here becomes 106. 106 becomes 118. 118 becomes 225. 225 becomes 245. 245 becomes 244. 244 becomes 229. 229 becomes 96. And the circle is complete. And then there's another table in here that starts with, well, character 160 is the inverse space, the solid square. It just stays there, but 224 becomes 231, and so on. We could follow that chain all the way through too. So this is where all the magic happens. One character gets converted into another character. And so I've recreated this in BASIC, but ultimately this is going to be written in assembly language. I'll show you that after. Okay, but what about our map that we created that was just character 20 and A0, which is the inverse space? So there's this little routine I wrote here from 100 to 120 that just goes through and checks each pair of characters. Here, we'll just run list 100 to 130. So we're just going to go through each character from, S is for the screen memory. So we're examining 40 characters here. So we're just going through and checking each pair. And if what is here and here are the same, then don't do anything. But whenever two characters are different next to each other, we're going to add 64 to the left hand of the pair. So we're just checking each pair. And that is what converts this 32 into a 96, which needs to be transformed. Whenever you have two blank squares in a row, you're not going to want to change this one, because when you scroll it to the left, you just want it to still be blank. But it's this one, when it scrolls to the left, the character has to move from this cell and start to grow into the cell beside it. And we tell it that by adding 64, which turns a space into a shifted space. And maybe this will make it more clear if we look at that conversion routine. And instead of just adding 64 whenever there's a difference between two adjacent characters, how about if we apply that to everything on the whole row? That is, all the 32s become 96s, all the spaces become shifted spaces, and all the inverse spaces become shifted inverse spaces. Okay, so we'll run it. And it looks just like before, but now if we go to 200 to do the transform, we'll see it's transformed the entire line. That's because there are no blank spaces anymore. So it's gone through here and converted every one of them. And if we keep doing that, see how it's transforming all of them. And then on the final one, everything goes back to normal. I hope that makes it more clear. We just have to do these leading spaces before the solids, and likewise the ending solids before the blank spaces. Only those ones can be transformed. All right, moving on. Okay, and now I've got Turbo Macro Pro loaded up, and we'll go through the assembly source code for the scroller. I don't think I've ever shown conditional assembly before with Turbo Macro Pro. It's not beautiful, but it works. So we've got some defines here. I can set PET currently to 0, that means C64. And ultimately when we do the PET build, we're going to switch that over to 1. And that's going to affect what is or isn't assembled into the final binary It's actually quite easy to do PET development on the Commodore 64 because they have so much in common, but the 64 is pretty much a superset of a Commodore PET. Not completely, but for the purposes of things like games and these kind of demos, there's a lot in common. And that's why it's possible for me to do the assembly on the 64 and then run the binary on the PET with very little trouble. Okay, and likewise, if we want to add what's called a basic stub, which makes the program runnable, it's quite a simple thing. I can flag that, but while I'm doing the testing, I actually don't want it runnable from basic instead. I want to just be able to start the assembly code directly. That's just a flag we'll have to set later. Here's the width of the map, and the map being that scroll text. When I first started working on this, I was actually thinking about making a smooth scrolling PET game to use this routine. It still hasn't happened, but that's why I'm using the term map. So that's just matching what we used in the editor just before. Now a few zero-page variables. The counter for the scrolling, that's going to go from 8 down to 1. The current X position in the map as we scroll through the map. So we're going to start at 0, top left corner, and then we're going to move to the right through it, character by character. ZP1, that's 0 page 1. I just have a habit of most of my 0 page variables, if they're general purpose, I just call them 0 page 1, 2, and 3, and so on. Because 0 page is at a premium, especially if you leave the basic enabled. So that's just a 0 page pointer that we'll be using. Okay, now we get into the conditional assembly. This means if equal to 0, this is not the best name for this sudo op. Now, this isn't actually a 6502 assembly command. This is an assembler directive. And basically, if PET is equal to 0, that means we're actually in C64 mode, then we're going to assemble to 0801 in memory, which is the start of C64 basic memory. And that's your classic place for a 64 program to load. And screen memory defaults to 400 hex here. And the map can live at 100, which is roughly 200 hex bytes, or should I say 512 decimal bytes later, or 511. Okay, and then endif just ends that definition. Unfortunately, we don't have an else construct in this, and that would have made things a little bit cleaner. But we're doing it old school. So if it is PET, if PET flag is set to 1, then these two go together. If we're running on the 64, this will assemble. If we want to build for PET, then this will. So basic memory moves down 400 bytes to 401. Screen memory moves way up to 8000, and that's fixed in the PET. The C64, you can actually tell the VIC to use a different area for screen memory, but on the PET, it's fixed here at 8000. And the map data, again, is going to be 1 FF hex bytes after. That's just the code goes here and then the map data after it. All right. Then this next chunk is just going to define where in memory each row, each line as I've called it here, of the scroll text is located, of the scroll bitmap, I guess I should call it, starting at the map location, and then at map plus the map width times 1, 2, 3, 4. The map is just stored linearly where whatever the map width is, like FE bytes in this case, FE bytes for the first row, and so on. So this just defines that. You could just use hex bytes, but it's cleaner to be using a bit of math to define it. Perhaps you could go crazy with macros and make this even cleaner, but I didn't do that. Okay, here's the basic stub. If we want the basic stub, then we're going to put a hex word. That's a 16-bit value with low byte and then high byte, pointing at basic end, which is down here, where we have 3 0 bytes in a row. And then another word which defines the basic line number. It's a C64 tradition to put the year of release as the line number. Then this next byte is the token for the sys command, SYS, which executes a machine language program. All we're doing is writing a bit of BASIC here, but doing it in hex in the assembly program. Looks kind of ugly, but it's a nice way of making a file runnable. And here we can nest these definitions. If it's a PET build, then this is the PETSCII code 1037, or the parameter, memory location decimal 1037. And it's easy to just write these bytes in hex. You just put hex, the high nibble is 3, and then the low nibble is just the decimal number that you want. So there you go, 1, 0, 3, and 7. That's actually this init label right here. This is where our machine language starts. Okay, and then end if equal to 0 for PET, then it's a 64 build, and then we do the 2061, which is the classic C64 start address. And then this 0 byte is the end of the basic stub, and then 2 more zeros indicate the end of basic. And then another end if, and our conditional assembly is done. Here's the proper code. Let's go through this quick. First, we're just going to clear the screen. 147, print the character, disable interrupts. If we're doing a C64 build, I just put this little bit of code in. That I've shown that before. That just allows you to hit restore and re-enter Turbo Macro Pro. That's just a debug thing, and it won't be included in the final PET build. Then we're going to set the map to start at the leftmost side, the scroll counter to start at 8, and that just counts the number of pixels scrolled before we have to do a shift. And then we're going to call this convert map routine, which does what I showed in the basic program. It just scans that entire map, looking at each pair, and whenever there is a change going from a blank to a solid or a solid to a blank, then it flags that by adding 64 so that our transform routine can act on some blank squares but not on others, and on some solid squares but not on the others. And here's our big loop. Here we're checking scroll count, and if it's 8, that's a special case. Every 8 pixels, we redraw the whole screen in a starting position shifted over, and the rest of the time we do the transform on it. So if it's not the special case, we're going to branch ahead, but this is, so like the first time it's run, so we're going to plot the whole screen. So it's a pretty simple routine. It's just a bit of brute force here, where we load the map index, we add 39, and transfer that to the X register. So we're going to draw from the right side of the screen to the left, and we do that because whenever you do indexing on 6502, it's generally faster to go from the high value down to 0, but because we can detect with no extra compare instruction hitting 0 or flipping over to negative 255 decimal or FF hex. So that's a common optimization. Start high, work down. We're going to load the data from the map and store it on the screen, row by row, and we do each row. So there's 7 of these. So for each row, we're just doing a load and a store. Now, of course, this could be written using nested loops. There's all kinds of ways you could do it, but that's slower. So this is being done for speed. And then we decrement X, and we also decrement Y. Check if the value is still positive, that is 0 or greater. And if it is, we loop back. So it just copies the full screen 40 characters. And branch plus, so if the branch plus is not true, then branch minus will be true. And that's a small optimization. I put bra here because that's short for branch always. And essentially the BMI, this code can't be executed unless the negative flag is set. So it's essentially a branch always. So that's every 8 characters that's executed. Then the rest of the time, this smooth scroll routine happens. And this is us doing that transform. there's that pattern of characters that gives the appearance of smooth scrolling. And we're going to do 120 characters at once, 119 down through 0. And we're just doing a loop. And this was as tight as I can make it. There's no decision making required while doing this whole transform. That's why it can be so smooth, and it can run within one frame, within one video frame. We just load the value currently on the screen into the X register, use that as an index on this conversion table, or I guess I could call it a transform table, and then we store it back in screen memory at the same location it was loaded from. And we do that in these 3 groups, 120. I'm actually converting 9 lines. I just noticed that, but I'm not going to change that because it works. At one point, I was scrolling more of the screen. I first wrote this routine like 12 years ago or something, so I don't really remember what my intentions were. But I think at one point, I wanted to be able to scroll as big an area of the screen as I could, and then I ended up just settling on the 7 rows. I'd have to go through and see how much screen actually could be scrolled at once. Okay, so you just decrement and branch if plus, and you just do that over and over again. So each byte is able to be converted with a single read, a table lookup, and then a store again. That's about as tight as it can go. Now, there's all kinds of other ways you could do this, but I think all of them would involve more code. If you can think of a faster way, then let me know. A faster way per character transform, that is. Okay, and now either way, our code comes to this point where we decrement the scroll count, and as long as it's not 0, we just go ahead. But if it is 0, we have scrolled a full 8 pixels. It's time to reset the scroll counter back up to 8, increment the map X counter, and then check, did we reach the end of the scroll text? This actually would normally be map width minus 39, but because I made the scroll FE hex bytes long, but didn't use all of it, so I tweaked this number a little bit so that the scroll wraps around quicker rather than just going on for a long time with a blank black screen before wrapping around. If we did reach the end, then we want to set map X back to 0 again. And then that's basically it. We're in an infinite loop here. We check for V blank. I'll look at that soon. And then we jump back to big loop all the way back up here. Do it all again. So that's basically all the code. Now I'll look at V blank. So we've got a PET version here that checks this particular bit, and that signals that the V blank phase has started on the PET. As the screen is drawn, usually 60 times a second, 60 hertz. Newer PETs with the large 12-inch screen, this bit indicates that the V-blank phase has started. Now, older PETs didn't have this feature, and that's why the scroller is not going to work properly on older PETs. You can't synchronize your code, or at least, well, not in this manner. Your code isn't going to be synchronized to the vertical blank, but that's necessary to have a very smooth scrolling effect. And here, the equivalent on the C64, I've shown this before, is checking this DO12, which is the raster register, which actually just allows you to outright read what line the 64 is currently drawing on the screen. I often choose FF just because that is a fine value. It works. So these aren't completely equivalent, but they do the same, for our purposes, they do the same job, whether you're on the PET or the C64. And then the last thing is this map conversion. This is what processes the map. So we just load up 0 page 1 with the top left corner of the map. And we want to process 7 rows. And we're going to start on the left in this case with the Y index set to 0. So we're going to do 7 repetitions of this, processing each line. And basically, we just check what is in the top left corner of the map, and we increment Y and compare it with the second character. And if they are the same, we don't need to do anything. We just branch ahead to head 1. But if they aren't, we're just going to clear carry, add with carry 64, and decrement Y, and store it back in the first square. Top left corner, compare it with the character to the right, and if they're different, we stash the value there plus 64. So a space 32 becomes a shifted space 96. They look identical, but they have a different value, and that's what allows this routine to work. And likewise, 160 is the inverse space as a solid square, and adding 64 gives us 224 decimal, which is a shifted reversed space. Okay, and then we just checked, is that whole row that we processed? If so, then we're going to advance to the next row to process, and we're going to count how many rows we've done and keep processing or we're done. And finally, here's the big table. And this is the equivalent of those arrays I showed you in the basic version. And I know it seems wasteful putting all these zeros in, but this is that classic trade-off between speed and memory use. It's just a 255 byte table, or 256 bytes. Probably doesn't even need to be quite that long, and that's where the magic happens. Okay, so we'll test it on the C64 first. If we go back arrow, Shift R, lets us load into RU RAM. I'm using the RAM expansion unit today, and that was map 2. And for the 64 version, we want to load that to OA00. And then we'll go back arrow 3 to build it, S to start. Let's see if it works. Yeah, there it is. And you notice it doesn't look as smooth as it should, and that's because of what I explained earlier, how the C64 does not have that single width pixel. It immediately jumps to a character that's twice as thick, then scrolls, and then when it gets to the end. So it has the effect of kind of making it look a little stuttery, but that'll work a lot better on the PET. Okay, restore to go back in. And now we're going to set both of these flags to 1. So we're going to be doing a PET build. I'm also going to reload the map to the PET location of 0600. Okay, we'll assemble back arrow 3. Now I'm actually going to pop into the monitor. Super Snapshot Monitor, go into the RAM expansion unit with star R0, and we can look at our code. Yeah, there's the basic header stub right there. Here's our assembly language. And we can look at the map at 0600. There it is, a bunch of 20s and A0, 2 zeros and A zeros. Let's find the end of that. It's a big map. There we go. And we've reached the end right here, where we start getting these zeros and Fs. Okay, and we're just going to save that, and let's call that wedding scroll. And we're going to save to device 8 from 0401, which is the start of the program, to the end of it, which is 10F8 or so. And there we go. I've saved it onto my SD card here. This is a micro IEC. You can also pick up a SD2 IEC. That's prettier, but functionally equivalent. Okay, now let's go try this on the PET. Okay, and here's the SD2 PET, which is a newly released SD card reader for the PET. It's fantastic. So I'm going to stick that SD card here in the reader, and while the PET is turned off, I'm going to plug it in the back where the disk drive goes. This little cable's for power, and this plugs into the disk drive interface. load up wedding scroll. And are we ready? Run. And there we go, just married. So that's it. Let's send our best wishes and congratulations to Jessica and Michael. And they've promised to send some video of the pets from the wedding reception when it happens next year. Thanks to my patrons for helping me make these videos. Thanks for watching, and we'll talk to you next time.